No, it's dimmer. Okay. You want to take yeah. 1 hour. Yeah. But, no, then if it is recording, then it's supposed to be fine. Full screen. This one, right? Yeah. Do I need to wait? Or you can no, wait, just better recording. Okay. This is better.
Yeah.
Yeah.
I'm not going to move around much, so not today. You all can hear me?
Yes.
Okay, lighting. So what I'm going to do is basically give you a crash course in what you all should know, okay, as a foundation for the lectures which Henrik is giving. And what I have done today is just taken up theorems from the first or I think second chapter of L.C. Evans. But I will quickly say what it means and also try to relate it for the junior participants with what they already know, so that when Henrik is taking the lectures, they are not completely lost, and they will realize that many of the things that are said here, in fact, you all have studied in MSc. Okay, so it is not going to be completely, unseen in that sense. You have seen some version, maybe you do not know the way we are doing it now. Okay, and what I would suggest is that you all should 100% go home and try to read that L.C. Evans chapter which I have taken these things from, and the proofs you will see, these are not very difficult. As he pointed out, you are just going to be do differentiation and maybe differentiating under integral sign, compactness. You are never going to go beyond that. Also, many times when we are talking about Laplace operator, okay, when we say Laplace operator is going to be what? Summation of d square by dxi square. So you all have already seen the Laplace operator in your Fourier analysis class. So like I'm appealing more to the junior students here. So they have already seen in the Fourier analysis class. So and when you are really finding out Laplacian of u, what are you doing? You are just going to take second derivatives in those xi directions. So as he pointed out today, it is always nicer to, if you want to understand what is really happening, to go to one dimension and try to think in terms of u double dash, u dash. Okay, so you get to know immediately how things look geometrically, and then you can kind of relate. Plus, once you go to one dimension, it is easier to imagine. You can think, and then you can slowly get into the higher variables, more than one variables, and proceed. So to begin with, I will just write down some of the differential equations. So first, partial differential equation, which in fact I think you all have already seen. This is a first order partial differential equation which you all must have seen in your differential equation course. Okay, so this is first order PDE, and here again I have written it for higher dimension. So we are looking for a solution u, which is a function of n plus 1 variable. It's a real valued function, and this is pointer, yeah. Okay. And for me it is easier to read from there, so I can see that. So here, you have x variable, which is called the space variable, and t is usually denotes time. This type of equation is called as transport equation. The way it is written is ut, so that is just partial derivative with respect to t variable, plus b dot d of u. So d of u is the usual notation for gradient. So and b is a given vector. Okay, so the simplest differential equation is of first order. One can write it as ut plus b dot du equal to 0, and one can try to solve this particular equation. As I said, in our differential equation class in MSc, they have already seen this, and one of the ways to do it is we try to solve it using ODE method. Okay, so what we are trying to do here, we try to write it as a function of one variable, or differential equation in one variable. So we define the function zx, which is equal to u of x plus sb plus t plus s, okay, for given xt. So you fix a point xt, and then what have I done? What I have done here is that this part here, this it's not thinking. Okay. So here, this part, what is this? This is nothing but
Right.
Yeah, it is just x plus sb, and second variable is t plus s. If you look at this original equation, it is much simpler. If you write it as a differential equation, it looks like that. But I can simplify it. I can write it as gradient of u dot 1d equal to 0. Okay, where the first variable is derivative. First derivative is derivative with respect to t variable. Okay. See, in that particular notation over there, if I consider it as a function of r, t and x, okay, if I consider it as a function of t and x, then my equation is nothing but gradient of u dot this particular vector is equal to 0. So what am I trying to find out? I am trying to find out u with the property that gradient of u dot product with a certain vector is equal to 0. But gradient of u dot product of given vector is nothing but directional derivative of u in that particular direction is equal to 0. So basically I want to find out a function u or a surface u such that this particular condition is satisfied. So what I do over here is I define a curve. So this is a curve which is in direction v1 or 1b, depending on whether you write t first or x first. And then I evaluate u along that curve. If I evaluate u along that curve and I differentiate with respect to s, I will get z dash s is equal to 0. So what does it mean? That z is constant along all these curves. So these are just going to be integral curves corresponding to the constant vector field 1b or b1, whatever, independent of whatever they write. So this is what in fact we had done in method of characteristics. Okay, you are trying to find a surface and then you are having the condition on the gradient of that particular vector field. So the first order PDE, the one which you already encountered, has this kind of a very simple geometric interpretation, and once you think of it in that way, you immediately get your solution. What happens is that z dash s is equal to 0, so z is going to be constant along all these integral lines corresponding to the given vector field. Okay, so you are having condition dot product is 0, so it is going to be, so these are, see, if I give a surface, then gradient factor is always going to be along the tangent. So tangent dot 1b is 0, means 1b is your normal vector. Okay, so your surface is such that at every point it is going to, your normal vector is going to be along 1b. Okay, so that's what you are doing. You are trying to find an integral surface, and that is what is your method of characteristic. So of course that is the geometry part. What we have is here already, I think it's fine. So here, how did we solve it? We get all these we'll get all these curves which are characteristic curves, and then you want to find a surface. So you put an initial condition which is going to be along initial curve, and then you get a proper surface which passes through a given initial condition. So this is what you all already are aware of. Okay. The second equation which we are going to use in this particular series of lectures is going to be Laplace equation. So here I have written the simplest form, Laplace u equal to 0, and Poisson's equation, Laplace u equal to f. Okay, till now I am not saying what is f, how much smooth u is, but we will assume it is C2 as long as we are able to differentiate it. Okay, so I believe you all are familiar with now what is Laplacian, right? So we all have already done that. This is the heat equation. I am just writing it down for you all to be able to compare. Okay, and this is the wave equation. Okay, so here this is so what happens is that here if you are able to solve the heat equation, if you are able to solve this particular, find a solution to this particular equation, what does it give you? It gives you the temperature at point x at any time t. Okay, that is what a solution to heat equation would give. Okay. If I am able to solve the wave equation, what would I get? I would get the position of the particle. Say if you have a vibrating string, what if I am solving this? It gives me the position of the particle x at a given time t. So the figure is of course wave. So it is vibrating string or vibrating wave which is moving, because once you have t, you have motion. Right? Here you have temperature which is changing. Here you have time, the movement which is there in time, right? So, but if you consider the stationary states of both these equations, it means once you say it is a stationary state, it means there is no change in time or there is no movement with time. So it means that derivative with respect to t is going to become 0, and you are in Laplace. Yes. Okay. So that is why Laplace u is usually, when you say Laplacian u, any equation which is formed using Laplacian u generally represents the equilibrium state of whatever problem we are concerned or dealing with. So that's why when I think when we are looking at this free boundary problem also, say once you have solved it, and when you're looking at this obstacle, you have the point of contact, but nothing is moving there. It is kind of stationary, right? So then that's why you get Laplacian. You don't get the t variable moving. So that's the equilibrium position, equilibrium state. That's what it denotes. Okay, so I will quickly now go through properties of functions which satisfy Laplace u equal to 0. So here, this we all know. Okay, so what do you mean by harmonic function? A function u which is C2 and satisfies Laplacian u equal to 0 is said to be harmonic. You have come across harmonic function already in your complex analysis class, okay, where you prove that the real part and complex part of analytic functions are harmonic. Okay. Remember one thing that I don't know whether you all have done it, but there is something which is called as harmonic conjugate, where you have a function which is harmonic and you try to construct a complex function which is, so you find u plus iv which is going to be harmonic conjugate. So I am going to relate it to what you all already know. So we come back to this thing about fundamental solution, and so here again I have just written it as heuristically. Okay. What we try to, so this one I think it is usually given as exercise for in MSc class, write the polar form of the Laplace operator. Okay, so I think we do it for R2. No, Rn. Yeah, they do it for Rn. And here, if you write down, so here, if you write it down in polar form, Rn theta, it is going to be d square u by dr square plus n minus 1 by r du by dr plus Laplacian. I have written with Laplacian theta. It means that it is going to be the surface Laplacian with respect to the theta coordinate. Okay, so it is not delta in delta sense, but it is the part which will involve only derivatives with respect to theta variable. Okay, and if we are trying to solve only for radial solutions, so solutions which are not going to depend on your theta variable, then the theta terms will vanish. I think there is a mixed term also, I'm not sure, but anyway, if it is going to be a function of r alone, you have no derivatives with respect to theta, and you are just left with an ordinary differential equation. You can just solve it without thinking about existence and all that, and because you see that once you have log r, you require to have, of course in this case in polar coordinates, r is always going to be greater than 0, and here yeah, you don't have r equal to 0 appearing at all once you have polar coordinates. So this is what actually gives us what we call as fundamental solutions. So this is one of the easiest way to derive it, trying to find a solution, that's all, without really bothering about anything else. So here, this particular function, phi x is equal to minus 1 by 2 pi log mod x, n equal to 2, and this is normalization. You divide it by volume of the unit ball or unit disk, and mod x power n minus 2. So this is what is called as fundamental solution of your Laplace operator. Okay. And this part I think is something which you all have solved. Dirichlet problem in the disk is something that is done in our MSc class, and here you see we define u of x equal to integral over Rn phi of x minus y fy e1. Okay. as so if you define it like this, then u is in C2 and minus Laplacian u equal to f in Rn. So here we usually assume that f is continuous and so this would be this is nothing which we recognize as convolution. Okay? This is convolution of phi convolved with f. That is what is going to be. If we try to prove it, okay, if we try to prove it, if you want to show that u is C2, okay, then it is not just going to be differentiation under the integral sign, because as you can see, when x is equal to y, okay, you will have problem over here, but you can either use the property of convolution or approximation, or if you have done the or as it happens in case of the Poisson kernel, you show that it is a good kernel, so you split the integral into region near origin and then outside. That is very nice. So it doesn't happen directly by integration under the differentiation under the integration sign. So it's not so I am going through this, but I want you all to go home and revise this. I'm not going to give the proof, but I'm saying that all these things will be required, and you just go home today and go through it, and then also go through what Henrik has done, so that tomorrow you will not feel more comfortable. Okay? So, you then think about and actually see why you cannot just directly differentiate under the integral sign. Try to reason it yourself, okay? Because in MSc you are just studying for exam. So for a change, now you are in study to understand why you are doing something, because then we have to pass the exam. So here it is fun. So here this is another thing which has come up in the lecture today morning, that Laplacian of phi. Laplacian of phi is Dirac measure. Usually many times there are some books who refer to it as Dirac function, Dirac delta function, but one should ideally refer to it as Dirac measure safely. It's not a function. And this I think I will explain in the next class, where what do you mean by this? Okay? What is Dirac measure? You all have seen that, right? How do you define Dirac measure? How do you define Dirac measure?
Functional distribution.
Yeah. Yeah, in sense of means it acts on function. Okay, but when you say it as a measure, what does it do? It assigns, it is one at one single point and it is zero everywhere else. So as a measure, it is a measure which is referred to as point mass. Okay, so you have Lebesgue measure, right? You know what is Lebesgue measure of a disk would be its area. Okay? So when I talk of Dirac measure, it is not Lebesgue measure. It is different from Lebesgue measure. So when you talk of Dirac measure here, so I have to make sense. Dirac measure, so Dirac at 0, so it is exactly 1 at 1 point, 0 and 0 everywhere else. Okay, so that is why he so the way you think of it is 1 at x equal to 0 and 0. Anyway, this is a bad way to write it. And this is a bad way to write it, but it is a point mass. That's better. And then one can think of it as a functional as well. So I think maybe briefly I will also talk of distribution. Well defined, and it's not today, but maybe sometime we will use weak solution also, because it helps to define weak solution. And here, so here when you are taking Laplacian of the fundamental solution, you see that the effect it is having is at origin it has becoming 1 and it is 0 everywhere. So it is not really a function, but it is a measure. Okay? So that is why one needs to be careful when we are talking of fundamental solution and you have all those convolutions here. Now I'll just go through some of the properties of harmonic function, every time reminding you that whatever you have studied for complex analytic function, in fact, is true for harmonic function as well. So here, one of the first properties is the mean value property. Okay, mean value property. So here, what does it mean? What does it mean? It means that in fact when you are this is similar to your Cauchy integral formula. Right? Your two Cauchy integral formula, the value inside the disk, any point in the disk is equal to 1/2 pi I integral of f on the boundary. So this is what one should think of. Of course, here x is center of the ball, but it is true even otherwise. You can take some other point, and many of as you prove for the complex analysis case, it is going to be true for harmonic function as well. The proof is straightforward. You just use integration by parts. You can see it is just 2 or 3 lines proof. You write this last equality, convert it to surface integral, and you will see it will come. And use the fact that the function is harmonic. Okay, so you will have partial derivative, normal derivative converted to Laplacian, and you will get your. So it is just 3 lines, but I do suggest that you work it out. Okay. The ninth thing is that the converse of mean value property is also true. So if you see it's a something being harmonic is equivalent to mean value property being satisfied in that particular domain. Okay, so what does it mean? That if you have a C2 function which satisfies the mean value quality, then it is going to be harmonic. So Laplacian is equal to 0. The proof of this is just 2 lines. Whatever if you write this correctly, you immediately see this is correct. So here in fact the proof you can so you define right? Yeah, you define it like this. You see here, I am writing this as a function of r here, and what we will do is if you do change of variable, then this r comes here, and you integrate over a ball of radius 1. Then you end up showing that phi dash r is equal to 0. You show phi dash r equal to 0, and you will get your mean value equality, because you will show that at one of the points it is going to be equal to ux. So it is an exercise which you all have to do. I am not going to do it in real practice. It is just 3-4 times. It's not hard. And if you will do this, then the converse also will follow. If you look at the proof of this one, converse is just one single line. Okay. Yeah, maximum principle. So again, let me go to what you all know for complex, for analytic function. We know that what do we know? What does the maximum principle say? Yes. Yes. What does the maximum principle in complex analysis say?
Equidipotence is maximum on the boundary of the
Yeah, so a function which is analytic attains a non-constant analytic function will attain its boundary or a maximum on the boundary of the set, right? Absolute of it. So similarly is true for harmonic function. So if it is harmonic, so here of course you have to assume that because you are talking of maximum, you want continuity up to the boundary. So see, when we are studying MSc, we can ignore many things, but now you have to start saying that okay, I said I want the maximum to exist, but then I want the function to be at least continuous up to the boundary. Like if I am going to say something about boundary, I want the function to be continuous up to the boundary. So I don't care about differentiability, but at least continuity. So then the result is same as what we know for complex analytic function. If omega is connected and there exists x naught belong to omega, such that ux naught is maximum of u, then u is constant. Okay, so this is called as strong maximum principle. So what does it say? It normally says that the maximum is achieved on the boundary, but it also says more that non-constant part. Okay, you assume, right? So that if it is there is a point in the interior where it has a maximum, then it is constant everywhere. So this is what is called as strong maximum principle. There will be situations where you can only get some inequalities. So those are weak maximum principle. Maybe you can read later on. But for present, I'm just going to do all of this. Yeah. Uniqueness part. So as the maximum principle immediately gives you uniqueness, because if I want to prove uniqueness, I will take difference of the two functions and apply the maximum principle. Because if I take the difference, if I have u1, u2 solution of the same equation, if I take difference of the two, then I will have Laplacian of u1 minus u2 equal to 0, u1 minus u2 equal to 0 on the boundary. So again I am back to harmonic function and I will get my condition. So uniqueness. So this is the regularity part. Means, of course, he is here. Yeah. The way the statement is written is depending on what they really use to prove regularity. Okay. So here, if U belongs to C omega, satisfies the yeah, sure.
You need it more than calculated.
Yeah, I think there is a
So,
yeah
is
for mean value property to hold.
no, generally for solutions to be C2. If you need U to be C2,
Here, with regularity or
if you need U to be C, if you were asking U to be C2, you need F to be Dini at least. And
C alpha.
C alpha is good, but Dini is the less. It's something that there's a counterexample actually. If you were to delve for you, this is a very this is not in the literature in general, but there's a counterexample. You have this. You can actually write it down. If you look at the following function, take a harmonic function at degree 2, homogeneous. So let's say x1 times x2, and then take the logarithm of the absolute value of x to power alpha. And x is less than 1, so this is negative, so I put the minus.
Yeah.
So for x less than 1. And this function is, if you take the Laplacian of 2, so this is a good exercise for you.
Yeah, I think
This is going to be a function f. So Laplacian is going to be a function f of x, and f of x actually is going to be continuous. This is continuous. alpha is in a range positive, and alpha is positive, it should be staying below 1. If it's below 1, it is continuous. You can see that when you do computations. But then this function is not C2. Because this is C2, exactly, but this log x is 0, this becomes infinite. So you can actually have this. When alpha is 1, the Laplacian is bounded. Okay. So this is going to be discontinuous when alpha is 1. With alpha below 1, you actually have very good regularity. But this is not enough. The function is at C2. So for C2, so U is not C2. But in order to get C2, you need alpha is larger than the alpha must be much less than 1.
A half maybe.
I don't know computations here, but probably have to go maybe below 0, negative or something. Yeah. But it's not that important. Important is that it gives you examples when you have right-hand side is continuous, but still you don't get the Laplacian so the function is C2. And that's it. In order to get continuity, you need that this guy should be C alpha or something, but the Dini continuity is the final stage. And Dini continuity is something that is written like this. So if f is, if, I'm saying that, no, if, not this f, but if generally f is Dini for C alpha, then U is C2 alpha, C2,
Yeah, alpha.
and then C2 alpha. If it's Dini, you write it C2. If it's C alpha, you write it C2 alpha. So Dini condition is something that is the function is Dini. If this is over 0 plus is bound, it means that this goes to 0 fast enough to make this integral to exist, and it's called Dini. So omega is Dini continuous. Big modulus of continuity. If the right hand side is Dini, then you're going to get C2. That actually is apparent in my computations. I did the integral. If you remember that, I did this integral, under the integral, sorry. And if it's Dini, you can actually make that computation to work. You get C2. And if it's C alpha, you can still make it much better. But you can not go below Dini. So it's common belief that continuity right inside gives C2, but it's not generally not true. It's very hard to come up with examples, and actually, these examples are not so, you don't see them in the literatures.
Yeah.
I don't think there is in the literature.
No, there is, no, I have not.
There is so there is in one of my papers, and then right after writing it, I realized that this also appears in the book of Van Malin and Shishinhan. You should look at that.
The geometric measure?
No, it is in the area, but the book is on PE. They have a book in PE. And that example also appears there, actually. I realized after I write it. Okay, sorry.
No, it's fine. Yeah, but the statement here is correct because it doesn't say, it only says that uniqueness if you are having these things. Then there exists at most one solution which is C2 omega.
Yes.
I mean,
You have to skip, you have to put a little bit more on that. Because you're saying C2.
No, what I'm saying is then there exists at most one solution, right? Means I'm not saying, I'm showing uniqueness. I don't care about existence.
Yeah, but even here you don't get it. Take this example. Take boundary values of this function. Then it's unique.
Oh, okay.
So you have to put the law in it. Or just say that there's uniqueness.
Yeah,
Skip that is C2. Either skip C2 or
There is uniqueness of the solution of this. Yeah, because once you take difference, it doesn't matter. It becomes harmonic.
yeah, you can do it with him,
Yeah.
there's uniqueness, but the claiming that it's C2, that's a little overstated. Generally. Because of the example. Well, I would say that your potential theories you were going in potential theory you were sorry.
No, it's fine. It's good to know. Please write it down and give it to me later on.
It's a good reputation.
Yeah, I think it's usually because I will come to that next part, and it is nice because here I'm doing just for harmonic functions, so things are kind of straightforward. So here I'm talking about regularity. I'm just talking about functions which are harmonic. So when there is no f appearing on the right hand side. So
you rewrote it.
yeah, when we do that other one, I think so. So here as you see the statement of the regularity over here, if u belongs to, this is just continuous on omega satisfies the mean value equality, mean value property for each ball, bx r subset of omega, then u belongs to C infinity of omega. Okay. So see, he is not writing in the statement it is harmonic, where we already showed that if it satisfies this mean value property, then it is going to be harmonic. But the advantage of writing it in this form is that this is the mean value property is exactly what you are going to use to show it is C infinity. You will differentiate the function and take the limit under the integral because and then show that the limit exists. Okay, so and again let me remind you, you all have done this when you derived higher order of Cauchy integral formulas. Okay. When you did complex analysis, complex analytic function, there you found out the Cauchy integral formula. Then you also check that f dash x also gives, you can write it in that Cauchy integral formula form. In fact, those are your coefficients of your Pau series expansion, Taylor's expansion. So your Taylor's expansion, when you did that, you found derivatives, right? And the derivatives come from integrating your Cauchy integral formula. That's how you got it. So this is reminiscent of that same idea. You're using your mean value property to show that the function is in fact going to be differentiable, and this is true for every ball. This is
regularity of the function simply means infinitely differentiable.
Yeah. Yes.
When you talk
Smoothness.
about surfaces, you say a surface is regular when it's non-vanishing derivatives.
Yeah, because then you are giving a structure, right?
Like
Because
we
when you're
want the
saying-
tangent plane to
Yeah.
exist.
Because you want to do analysis, so that's that regularity is because you're writing it as a graph, or you want to say that it's a regular value or critical value. So that's different. But generally, when you say regularity, you are saying smoothness, and that regularity also means it is smooth because you have one fixed normal direction, and you can differentiate as many times as you want in all of the tangential directions. So you will get a surface which is smooth if you have that. So regularity still means the same, but when you are talking of regular surface in terms of graph, then you want the value to be a regular value for the levels. So it is still smooth in principle. Okay. So here this is estimates on derivative. Again, this is one should think of it as your your Cauchy estimates which you did for harmonic function. Whatever you got for your first derivative, for f, by iteration you do it for all higher order derivatives. This is exactly what it is. Okay? Only thing is, you do not have tools of analyticity. You are doing everything at real analysis level, and the advantage is that you are having your mean value property. You just work with mean value property and you will get this estimate. You should go and look at the proof. All this is from LC Evans, and he has given it proof. I'm just trying to show you all that it is very closely related to what you all already know. Lewis theorem. What is Lewis theorem? A bounded entire function is constant, right? So same thing. So here bounded harmonic function is constant. So you see what holds for the real and imaginary part holds even for one part of that particular function. Again, the proof would be using your mean value property, right? Okay. Analyticity. Okay. So what do you mean? So here our u is real value function. Okay. So there is always this kind of question. So what do you mean by saying that u is analytic? Okay. When u is a real value function, it means that you have a power series expansion around every point for that function. Okay. So when you talk of real analytic functions, it means that it has power series expansion, and this should be expected because as I already told you, we said that it is C infinity. Okay, but in process of showing it is C infinity, we are going to use our mean value property, and we know that, means that's why I started with your complex analytic functions, right? Because there, when you calculated your Taylor's expansion, you showed that your coefficients are obtained by your Cauchy integral formula. You have Fn is equal to integral of Fn minus 1 upon, yeah? So that's how you got your coefficients. And here also, if the same property holds, in fact, you will get your coefficients from your mean value property around that particular point, which you want to write down your Taylor series. Okay. So you see, though all this thing is in Rn, but I am telling you everything for C, okay, and just telling you that you should relate it to what you already know, because it is not very different from that. The underlying idea is very similar, the proofs are also very similar, and if you will work like that, you will understand faster, okay? And it will be clear what is happening. So you can see this right down, okay. Yeah. And this is Harnack's inequality. So here, what does it say? So it says that for each connected open set K, which is compactly, when you write double subset, it means it's compactly contained in omega, then there exists a